So we're going to talk about some properties that apply to this new log function that we learned about. So these are three main properties that we can use to simplify log expressions. So we have the addition property, the subtraction property, and the power property. So the addition property states that if you add two logs together and they have the same base, then we can actually combine them into one log by multiplying their inputs. So for example, if I had like log base 2 of 4 plus log base 2 of 2, this is the same as saying log base 2 of 8, because 4 times 2 is 8. And you can see that working here because we know log base 2 of 4 is 2, and log base 2 of 2 is 1. And on the right side, we know that log base 2 of 8 is 3. So 2 plus 1, I think, is 3, right? So you can kind of see how this is working. It's very similar to, if you think back to exponents, we know that b to the power of x times b to the power of y equals b to the power of x plus y. And since log is the inverses of exponentials, it kind of has an inverse property to go along with it. So when you add two logs together, you can multiply their inputs, just like when you have two exponentials multiply together, you can add the exponents. So then the subtraction property is really the same as the top property, but now instead of multiplication, we have division. So we can write like log base 3 of 27 minus log base 3 of 9. This is going to equal log base 3 of 27 divided by 9, that's 3. And again, so 3 to the third makes 27, so this is 3. 3 squared makes 9, so this is 2. And log base 3 of 3 is 1. And then the same idea is happening here, right? So we know that if we have b to the x divided by b to the y, that makes b to the power of x minus y. So again, same property, but in an inverse kind of way. And then this last one, again, if you think about it, it's actually just an application of the addition property again. This is saying if we have something multiplied by a log, then we can move this thing into the exponent, or vice versa, and move it down. And make it like log base b of x to the power of a. Notice it's not like the whole log is raised to the exponent, it's x to the a and then log of that. And this is, again, similar to when you have this thing going on. So b to the x raised to the y is the same as b to the x times y. So again, another property that's similar to an exponential property that we already know. So for instance, if we had 2 times log base 2 of 32, this is the same as log base 2 of 32 squared. And 32 squared is, I know this, times 32, 1024. So on the right side we have, so log base 2 of 32 is 5, because 2 to the 5th is 32. So this is the same as 2 times 5. And this is log base 2 of 1024. And I'm sure you suspected, but that actually equals 10. So 2 times 5 equals 10. Log base 2 of 1024 is 10, so they're the same thing. So we can use these to condense logs into a single logarithm, which is going to be extremely helpful when we start solving log equations, because we don't want to have multiple logs showing up on the same side of the equation. So this allows us to condense it into one log. Now notice, of course, the bases are the same on all these. If the bases were different, we wouldn't use the log properties, and you actually wouldn't be able to solve things like that using standard algebraic techniques. But these we can. So here I have log base 3 of 4x minus 2 log base 3 of 8. And I just want to condense it into one logarithm. So for starters, I'll notice I have subtraction here, but I can't use the subtraction property because of that coefficient. So that's really important to remember, is that the subtraction and the addition properties require that these have coefficients of 1. Or technically the same coefficient, but it's easiest if it's just 1. So can't use subtraction with a coefficient. But I do have a property that allows me to deal with coefficients. So I can make this coefficient into an exponent and rewrite this as log base 3 of 4x minus log base 3 of 8 squared. Alright? And then 8 squared is 64. So log of 4x minus log base 3 of 64. And now I can use the subtraction property and write this as log base 3 of 4x divided by 64. And then I'm just going to simplify that fraction to 1x over 16. Alright, so now we have it as a single logarithm. So the second one, I have log base 5 of 100 minus log base 5 of 16 all over 2. Again, the same thing is going to apply here. I can't use the subtraction property here, so it's divided by 2, but another way to write this, something divided by 2, and an easier way to write this in turn, if we're dealing with logs, is 1/2 times log base 5 of 16. Because that's the same thing. Now, just like I did on the last one, I'm going to make this the exponent. So I have log base 5 100 minus log base 5 of 16 to the 1/2. Okay, quick quiz time. What is the same as 16 to the 1/2? Okay, if you said square root of 16, you're right. So it's log base 5 of 100 minus log base 5 of square root 16. And now I know that square root of 16 is 4, so I have log of 100 minus log 4. So now I can divide the two. 100 divided by 4. And that equals 25, so log base 5 of 25. And we know that log base 5 of 25 is 2, because 5 squared is 25. So, you might not have believed this when we started, but if I type this whole ugly thing into a calculator, it equals 2, because we can simplify it down to 2. So, another useful application of log properties, it becomes more useful as you go on into higher levels of math, is expanding logs into many logarithmic expressions. So rather than have one log, I want to reverse it and go back to something that looks more like this first example. As for why you'd want to do this, well, when you go on to take calculus and you deal with these things called derivatives and integrals, it's much easier to apply a derivative or an integral to something in this form as opposed to something in this form. For now, it's just a fun exercise in you're going to be better at simplifying these if you also know how to reverse it and go backwards. All right, it makes you stronger on both ends. So here I have 3 times log base 5 of 2x over 1. So I can't apply any of my addition and subtraction properties unless I don't have a coefficient here. So I'm going to make this log base 5 of 2x over y to the third. And then that exponent can be applied to each term inside that parentheses. So I have log base 5 of 8x cubed over y cubed. And now, so one way to write 8x cubed over y cubed would be 8 times x cubed times 1 over y cubed. And I'm going to write it like that because this shows me that I can now split this into 3 separate logs. So I have log 8 plus log of x cubed. And then since this is 1 over y cubed, I'm just going to write it as 1 minus log of y cubed. Oh, I forgot to write my base. It's log base 5. And then I'm going to bring these 3's back to the front and make my final expanded log base 5 of 8 plus 3 log base 5 of x minus 3 log base 5 of y. So from here I couldn't expand it any further. I mean, I suppose I could write 3 log x as log 5x plus log 5x plus log 5x, but that would just be expanding it to a more complicated point. So this is like the simplest expanded version of it. Okay, so then last we have log base 7 of 25x to the 4th all over 2. So again, it's helpful to write this as 1/2 times log base 7 of 25x to the 4th. Because this kind of shows me that this is really just a coefficient, and therefore I can make it an exponent. So I have log base 7 of 25x to the 4th raised to the 1/2. But I know that raising something to the 1/2 is the same as square rooting it. So it's the same as log base 7 of square root of 25x to the 4th. And now I can square root both of those. Those are both perfectly nice square numbers. So I get log base 5 of 5x squared. Oh, that's base 7, not base 5. Right? And now I can use my multiplication property in reverse to make this log base 7 of 5 plus log base 7 of x squared. And then I'm just going to bring the 2 to the front and get log base 7 of 5 plus 2 log base 7 of x. And this would be considered a simplified but expanded logarithm. One good thing to realize about these log properties, so if I look at this part of the expression, and I have log base 7 of 5x squared, so the whole thing isn't squared, only the x is squared, so I can't bring the 2 down in this scenario and make this 2 log 7 of 5x. And you can see that because when we split it up, we got something that was very different. Because this exponent isn't applying to the 5 also. So this would only work if this was like log base 7 of 25x. Or if it was 25x squared, then I could square root the 5 and bring it in front. But I was trying to write like 5x in parentheses squared. But that's not what we had. Okay. If you would like to continue watching, I'm actually going to go through a short little algebraic proof of this first property. If that interests you, you can keep watching. If not, this is everything you need for the homework. But if you're just curious about why do these log properties even work, then I'm going to show you how the first one works, because the second and third ones are just applications of the first one. All right, those of you that stayed with me. So we're trying to show that log of x plus log of y equals log of x times y. So to do this, I'm going to define a couple of things. I'm going to say that log of x equals to some number w, and log of y equals to some number c, right? I don't know what those numbers are, but the whole point of this is that I keep it generic so that my argument sort of works. So then, we know that log of x plus log of y equals w plus z. So now I'm going to do a little algebra trick. I'm going to say that both sides of this equation are exponents with a base of b. So this is b to the power of log x plus log y equals b to the power of w plus z. I'm allowed to do this because I did the same thing to both sides. So on the left side, if I'm adding two exponents together, that's the same as multiplying their bases. So I'm going to write this as b to the log x times b to the log y equals b to the w plus z. Now, if you remember the definition of a log, if I do a number and then raise it to the power of log of that number, those are inverse operations, and I'm just going to end up with x. And here, the same thing. So I end up with x times y equals b to the w plus z. And then lastly, I'm going to take the log base b of both sides. So I have log base b of x times y equals log base b of b to the w plus z. Right? Now, I can bring this part of the log expression to the front. Oh, wait, no, I can't do that actually because we haven't proved that yet. But I do know by the definition of a log. So, like, if this was log base 2 of 2 to the 20th, I know that the number I raised 2 to the 20th to get 2 to the 20th is 2. So these, again, are inverses, and they're going to cancel each other out. So I get log base b of xy equals w plus z. Oh, wait, but what were w plus z? Log of x and log of y. So substituting back in, we have shown that these two things, these two quantities, are equal, which is what we wanted. So, short little QED little box